Okay. Good afternoon, everybody. So about to start. Before I introduce Spiros, I want to thank everybody for coming to these semester seminars. We had many talks about the cosmos, how the whole universe works, and how the social structure works, and how not to have friends. So we're going to finish today with a very important topic that all of the talks we heard this semester is about computing. And if your computers don't work because they have malware, that's the end of the story. So Spiros is going to talk about that. It's a pleasure to introduce Spiros, a good friend of mine from Philadelphia. We haven't done work together, but we have a lot of discussions about other things. He's a professor of computer science at Drexel University and the senior associate dean of computing in the College of Computing Informatics. That includes large data and data science, something very relevant to us. He has his PhD from Toronto in computer science. And now, as I said, he's at Drexel. His expertise is in everything that includes software, malware detection, automatic computing, software design architecture, reverse engineering, software security, genetic algorithms, and software engineering education. And as I said, today he's going to talk about detecting malware. And let's hear Spiros.
Okay. Thank you for the introduction, and thank you everyone for attending the talk. I know it's the last week of the term, and you're probably busy preparing for exams and taking finals. Some of you, I imagine, are students. So I wanted to talk a little bit about this work. It's collaborative work, of course. Most interesting work is. A lot of this work is due to the efforts of my PhD student, Ray Kanzanes, and he is co-advised by me. I'm at the College of Computing and Informatics, and Moshe Kam, who's at the College of Engineering at Drexel. Moshe Kam just told me that he is the new dean of engineering at NJIT. And so now poor Ray Kanzanes has two deans for advisors, and probably the most difficult thing he's going to do is to get his PhD is to find a time where he can schedule his final exam. Also related to this project is Dr. Chris Roris, who is a former mathematician at Drexel, who's now at the University of Pennsylvania, and he's worked on some aspects of this project as well. So today's topic is probably not that familiar to most of you, although I imagine that everyone in here uses antivirus software. There was a story recently about an Android application for malware protection that you probably read about, and all this Android application did was it had an icon, and you could enable it by clicking on it, and then it would say protected, or you could click on it again and disable it, and it would be non-protected. This application got 4.5 stars out of 5 in reviews for Android, and it was one of the most popular downloads. I think the author of this software made $30,000 by selling it for, I think, 99 cents or $3 a pop from Australia. And that's all the software did. It changed the icon from enabled to disabled. And of course, the users were very excited because they said, this is fantastic, it's so easy to use, and my Android app has not had malware since I installed it. Okay. So, so because there's a lot of confusion as to what malware does and what malware protection is, and so people get a false sense of security. Okay, so I want to talk about how much can we do to automatically detect malware, the presence of malware on our machines, and that could be on your Android app, on your Android phone, it could be on your laptop, it could be a server that you're running, it could be a cloud computing system that you're maintaining, finding out if there's the presence of malware on that system in real time. The emphasis here is real time. As you know, if you get infected by malware, you might have it on your machine for weeks, months, years. You probably, a lot of you now in this room probably have malware on your machine that's dormant and waiting to get instructions from the mothership to do something using your cycles. So I want to define malware as basically software that does something that's not in the interest of the system user or owner. Okay, now that's a very general definition, and one could say, well, then is it malware, for example, if you work for a company and let's say your boss wants to spy on you, right? So from my perspective as an employee, maybe I feel like that's malware. Maybe from the boss's perspective, it's not malware. But anyway, it's software that does something, let's say, clandestine, something. So it's a elusive definition. So there are many types of malware out there. It's not all the same. Not all malware is dangerous. Not all malware destroys your machine. A lot of malware just doesn't do much. But some of it could be used for things like espionage, sabotage, ransom. Ransom is sort of one of my favorites because someone could install malware on your machine, encrypt everything on your machine, and say, okay, I'll give you the key if you give me a certain amount of money, right? And that's sort of called ransomware. A lot of malware is just related to distributed computing. It installs bots on your computer, which are these dormant applications, these dormant pieces of software that really do nothing except wait. And then one day, maybe they'll get a signal from the mother bot saying, okay, now it's time to do a distributed denial of service attack on Amazon, something like that. You can also look at malware based on its categories. What are the types of things that malware does? Sometimes malware is a Trojan horse. So really, you get an application that looks like it's going to do something like allow you to play a nice video game, but really, in addition to playing the video game, it's deleting important files on your machine. Sometimes you can categorize malware based on what it does, how it replicates. A virus replicates automatically, but so does a worm. But the difference is that the worm doesn't need an action from the user to replicate, whereas a virus does. You sort of have to click on it in order to enable it. Some malware allows you to root a device or a system. Sometimes the malware is spyware, where basically it's doing key logging and trying to figure out what kinds of things you're typing and recording those things. And maybe while you're typing, it'll find out that you're going to your bank. And if it knows that it's going to that website, then it could say, well, if there's some text that you typed after you went to that URL, maybe that's your password. And so it'll take that information and try to use it to log into your account. And Pavlos was asking me on my way over, what is an Easter egg? And, it was just Easter now. So an Easter egg is, you have some application that does one thing, but also can do other things that you don't know about. And sometimes those are nice surprises and sometimes not so great surprises. And a famous example of an Easter egg was in Microsoft Excel. I don't know how many of you know this, but Microsoft Excel, a former version of it, if you had an elaborate control sequence, Control Alt, foot pedal A, it would convert your Excel spreadsheet into a flight simulator. I've actually tried this. It was a lot of fun. And you can actually fly around, and the names of the developers of Excel showed up on mountains as you were going over the landscape. And so that's a nice example of an Easter egg application. All right, so we know that malware is big business because, we read newspapers. But you can go to the Common Vulnerabilities and Exposures website hosted by MITRE and find out all of the known vulnerabilities in software that exist. Now, vulnerability is not exactly the same thing as malware. I don't know if you know the distinction, but a vulnerability is you have a regular program, and that program has some security holes in it. And maybe those security holes enable people to take control of your machine and install malware. Right? We'll get into that a little bit later in the talk, but it's a little bit different from malware. So a lot of people say, well, you could solve the malware problem if you just make sure that every application that runs on your machine is authorized. So there's a lot of crypto processors that are on modern hardware that enable you to verify with cryptography that a particular application is authorized to run on your host. Well, if you're using that idea, you'll catch a lot of malware that sort of is dormant on your machine when you execute it. But what if you have an application like a web server that is authorized, but that website server has a vulnerability, and someone is able to pass data to the web server that essentially enables them to get a shell access to that machine as root. This can happen. So vulnerability is sort of an orthogonal thing to malware, right? It's the enabling mechanism. And when you hear about vulnerabilities, you often hear terms like buffer overflow attacks, and we'll get into that a little bit in the talk, and SQL injections and terms like that. This graph shows you what's going on in terms of vulnerabilities. This is not malware. This is holes in computing systems that we know of. And if you see from 1999, the new CV identifiers were on the order of 1,000 to 2,000. By the time it got up to 2008, it got to 7,000. Then the economy kind of tanked, and so did the new vulnerabilities, right? I guess people were busy trying to find a job or doing other things. Companies were closing. But now that the economy is picking up, guess what? The vulnerabilities are also inching up on that curve. And there are obviously vulnerabilities that have to do with weaknesses in the programming language. Okay, so some of you who have done work in secure programming probably know that there are certain routines like string copy that you should never use if you're a C programmer, right? And what are the side effects of using that incorrectly? And you should use str-in copy instead, for example. And of course, even if you have good technology, if you have good software that doesn't have, let's say, a lot of vulnerabilities, you could still have people misuse your computing systems by things like social engineering, right? So tricking you into telling me what your password is, or someone calling you up and saying, there was an example of people getting calls saying, oh, I really need to do something because your bank account is in trouble. Please give me the maiden name of your mother. And you're sitting there saying, oh, okay, I guess if I need to do this, I'll give you the name. And obviously, then they go and they have access to your bank account. So I just wanted to give you one example of, let's say, a buffer overflow attack, because this is something that you've probably heard of. Do we have any experts in buffer overflow attacks in the audience? Right? No. Okay. So this is good. But you've heard of it, right? Right. Okay. So the idea here is this is a very sort of dangerous type of thing. It will enable you to, let's say you're running a regular old web application, and you have fields in the web application where you type in your name, right? Name, address. You've used the types of things. Have you ever tried to type into that field something exceedingly long, like, select all the text in Moby Dick and paste that into your name? Right? A lot of systems will just say, too long, or it'll take the first 8 characters of that and say, okay, that's your name. But some systems might crash if you do that, right? It's just that no one really does that, but if you wanted to do strange things on computing systems, you would start doing things. Now imagine that instead of pasting Moby Dick into that field, I pasted the hexadecimal encoding of opening a Unix shell, all right? Just some machine instructions. I wonder what that would do. Or maybe even worse than that, a really long name like mine, followed by a bunch, or Pavlos, or my name and Pavlos concatenated, followed by the hexadecimal encoding of a command shell. Well, I'm going to show you that if you do that and you understand a little bit about the layout, the machine layout of the particular host you're attacking, you can take control of that host by just passing it that string, right? So what it would do is, This is your process address space. So when you run a program, you know that every time you call a function, you put a particular activation record on the stack, right? And it keeps store of your local variables. And one of the things that it keeps track of is the return address. So when I call a function, it goes off, it starts executing some code. When it's done executing that code, it has to roll back to where it came from. That's the return address. So imagine if I can overwrite that return address and just put a new address in there that instead of going back to where I came from, takes me to the string that I just passed. And then imagine that the program that I'm attacking has root privilege. And imagine that if I could redirect the return address to open a new shell, and I'm passing the hexadecimal code to run the shell, and it opens that shell on my display, that I will have root access to the machine, right? So that's sort of the conceptually what happens. And sort of in a diagrammatic fashion, if you look at the buffer here, okay, I put my name, Spiros Mancoridis, followed by Pavlos Protopopoulos, followed by the code, the hexadecimal encoding of the shell. And that's going to be longer than the buffer that was originally designed for that application, right? But I'm not doing bounds checking because I have a vulnerability in my code. So what it'll do is it'll start filling in that buffer. And when it runs out of memory, it's going to spill over onto the stack. And what it does is, it'll clobber variable I. That was a local variable in my function. And then it'll clobber some pointer that I had as a local variable in my function. And then another pointer. And then it finally gets to the return address. And that's where, that's sort of housekeeping, trying to keep track of where do I go after I make a call to this particular function that we're running now. And instead of returning to the right machine instruction to execute the rest of the program, it takes that instruction and it points it back to the buffer. So then the computer system says, okay, that's, I guess, where I came from, so I should continue running those instructions. And it's going to run the instructions to open the shell. And because this is a privileged application running as root, I will get root shell. Okay? So that's an example of a vulnerability using a buffer overflow attack. And it's one way that you can get control of the system. Once I have root on your machine in root shell, I can install 10,000 bots. I can delete files. I can do whatever I want. Right? All right, so who does this stuff? If you read the newspapers, you'll see nation states do it, corporations, cyber criminals. There are cyber organizations that will sell you botnet access to hosts that are vulnerable. Individuals might do it just to show that they can. And why people do these things, a lot of it has to do with the economic reward of selling essentially access to vulnerabilities. They might have a whole database of known vulnerabilities on systems, and they'll say, hey, I'll sell them to you. And eventually, of course, the community finds out about them, and they go onto the CVE, and the CVE publishes a patch for that vulnerability so that you could patch your systems, and your system administrator should be doing that. A lot of it is to generate spam, to put spam bots on your machine so that it could spam other users or send bulk garbage mails or junk mail. Okay. It's really a big business. At this point, you're all wondering, why is this a big problem? I mean, I'm running antivirus on my machine. My system administrator is running antivirus. What's going on here? Okay. Well, if you look at the targeted attacks per day, we have about 116. This is 2013 data. That's up 42%. About 3.4 million bot zombies, 74,000 malicious domains, 14 exploited zero-day vulnerabilities. That's zero-day means these are vulnerabilities in code that are being exposed that people don't know about. They're zero-day because companies like McAfee don't know about them yet. Okay, when they find out about them, they're going to say, okay, I'm going to create a signature for that particular exploit or malware, and then I'm going to push it onto all of your machines. So next time it shows up, it'll say, okay, I found that malware. And if you look at the data breaches in targeted industries for malware, a lot of it is for healthcare, getting information, records about patients, education, maybe finding out people's grades, changing people's grades, government, defacing websites, targeting various industries. And what's kind of frightening about the trend is that, you know, you might think that the world is highly computerized now, but actually relatively it's not, okay? So if you look at, for example, the power grid, do you think that's highly computerized? If you think about the FAA and how aviation is controlled, is that highly computerized? Some people will say yes and no. Like compared to 1930, yeah, it's highly computerized. But compared to the potential of how computerized it could get, we're still kind of in the Stone Ages, right? The smart grid that they talk about is sort of more of a dream at this point rather than a reality. If you look at how aircraft is monitored and controlled during flight, it's still done in a very old-fashioned way. Some of the equipment that's used by the FAA was designed in the 50s and is still manufactured to those specifications. So we're adopting computerization in a very slow way. And part of it is this notion of trust. And the trust could be either we don't trust the software because it's vulnerable to attack, but sometimes we don't trust the software because it's very brittle, okay? So unlike other engineering artifacts, software is one of those things that tends to explode very easily, okay? So it's, you know that when you're writing your program or using someone's program and it stops working, it just, poof, you know, freezes your computer or just stops executing. And that's a completely different experience from, let's say, a bridge malfunctioning, right? It would be the equivalent of I'm crossing a bridge and all of a sudden it sort of disintegrates, right? So software doesn't have these warning signs that, you know, I'm failing or I'm on the verge of failing. It just fails, and it's because of the nature of software. So if you look at the traditional defenses for malware, it has to do with having secure policies, having secure programming practices, using network intrusion detection systems, using antivirus programs like the one you have on your machines, and using things like trusted computing where you only allow trusted signed code to execute on your machine. So this is standard technology that everyone uses today, okay? Now, if you look at antivirus programs, and you know, I'll give you examples of Symantec and McAfee, those antivirus programs are basically looking for byte sequences on your machine, okay? And what happens is, I write a piece of malware, McAfee finds out about it, they scan the binaries and they say, you know what, if you find this sequence of code, that's a signature, I'll push it on to, let's say, your machine, and then if that shows up in your memory or on your disk, I will say definitively that malware is present, okay? And that works great, right? It's got very low false positive. If it says it's malware, it's definitely malware, right? So why isn't this enough? Why can't we just say, all right, it's a solved problem. If there's malware on my machine and I run it, my antivirus will tell me, and it has very low false positive rate. So why can't we just say we've won? What's going on? Do we know? Okay, the timing issue. So by the time Symantec gets a hold of that malware in their lab, create the signature, and push it to everyone's laptop, it takes maybe an hour or 10 days. In those days, you're vulnerable, okay? Is that the only problem, timing? It's not the only problem. Malware authors are very creative, okay? So first of all of this malware detection analysis, it's completely an arms race. As soon as the malware hackers do something, the protection people do something. Then the malware hackers do something more clever, and then the protection people do something more clever. So first thing malware authors do is they create a polymorphic virus. Okay, a polymorphic virus is essentially something that encrypts itself. So when it replicates and it's sitting on your disk, it's in an encrypted form. So when the antivirus program is scanning your disk, it's not going to complain about that because it's going to say, well, this is not exactly the signature I was looking for. It's encrypted. And it decrypts right before it executes, okay? All right, so what did the malware detection people do? They said, okay, we'll look for signatures of encryptors and decryptors, right? So it's an arms race. So what do you think the malware people did after that? And it wasn't encrypt the encryptor. All right, they created something called a polymorphic virus, metamorphic virus. So there's Kafka up there from Metamorphosis. And the metamorphic virus is even more surreptitious because what it does is every time it copies itself, it creates a copy that's a little bit different from its original. So it'll take, let's say, the malware, and it'll reorder the location of the variables. It'll add some junk code that really doesn't do anything. It'll move code around, move the location of the functions around. So it'll do a semantics preserving transformation of the binary code, and then some. And then it'll replicate. So what happens to antivirus companies is they'll say, well, I did an update for Pavlov's recent virus, but what they don't know is that every time that virus replicated, it became a different virus. And so it's futile to try to keep track of these viruses and updates, because every time Pavlov's malware is going to replicate, it's going to create another unique copy of that. So you're going to have millions of signatures, variants on that original malware that are only detectable on your machine, right? So it's almost like a denial of service attack on antivirus providers. So once you look at those types of viruses, you sort of say, well, I think signature-based detection is sort of old technology by now, right? It's very easily defeated. So the next generation of protection mechanisms have to take into account things that are behavioral. And as soon as you take into account things that are behavioral, you're going to start having, unfortunately, things like false positives, right? The beautiful thing about antivirus up to now is almost no false positives. If you found malware, it was definitely malware. All right, so the work that I'm going to be talking about is creating a safety net. Once malware goes through the firewall and through the antivirus of your target host, not if it goes through, once it goes through, what do we do, right? We want the host to be able to quickly detect the presence of malware with a low false positive rate, and if it's clever enough to also say what kind of malware it is, right? Because it might not be able to say, as, for example, McAfee does, to say it's this specific instance of malware. It might be able to say at best that it's some variant of Stuxnet, okay? So my goal is to create something that's online, real-time, and something that's low cost, where you can control the false alarm rating, et cetera. Okay, so I'm going to talk about two approaches for detection, and then I'm going to talk about an approach for going beyond. Detection is a simple formulation. In a particular moment in time, does my system have malware on it or not? So it's a binary detection, right? Classification is more like, if I have detected the presence of malware, can I also say something about the nature of the malware? What family of malware does it come from? All right, so the first approach is more of an intuitive approach so that you can understand how this general mechanism works, and then we'll get into more esoteric approaches. So if you're doing it very naively, you can say, I'm going to start monitoring things about my system, all right? And think about the analogy as sort of if I'm doing health monitoring for a person, okay? I'm going to start monitoring blood pressure, temperature, things like that. And then I hopefully can detect when someone is, entering the state of cardiac arrest, okay? So in computer systems, you have lots of sensors that you can deploy. One of them could be telling you what kind of CPU usage your system is using, what kind of memory usage. So imagine that you have hundreds of sensors telling you about things that your system is doing. All right, now, in this simple example, because I want to render it in 2 dimensions, let's assume we only have 2 sensors, one for keeping track of CPU usage and one for keeping track of memory. And those green dots represent points in that space, in that 2-dimensional space, where everything on your system seems to be just fine, okay? If I take all those points and I enclose them in a rectangle, I might say, okay, I'm overestimating the space, and anything inside that rectangle means I'm doing great. But if I start monitoring the system and I exceed the boundaries of the rectangle, then I start getting worried that maybe something malicious is going on, because all of a sudden my CPU usage or my memory usage is unusual. And of course, the problem is that it's not a very good approximation because the data looks nothing like a rectangle. Someone would say, well, what about a more compact representation? And if you want to take the most compact geometric enclosure that's convex, it's the convex hull. So maybe someone will say, well, what about the convex hull? We can use that as an approximation. And for those of you who don't remember, a convex hull is a pretty simple definition. You take 2 points in a set. If you could draw a line between those 2 points and the line never leaves the set boundaries, then it's convex for any 2 points. All right? So basically, it has no sort of no gulfs in the set. And the thing about this is if you're going to be using just one sensor, you're talking about a one-dimensional convex hull. If you have 2 sensors, you're talking about a 2-dimensional convex hull. But in reality, if we're going to do this, we're going to have 1,000 sensors. So you want to talk about a 1,000-dimension convex hull, right? So unvisualizable and kind of hairy and complicated. So a one-dimensional convex hull is just a line. If you're somewhere in that line, then you're healthy. If you're not on that line, then you're not. In a 2-dimensional case, imagine that I'm taking, those are my healthy points. I take a rubber band and I put it around them and I let it go. It'll snap to something that looks like this. That's a 2-dimensional convex hull. All the points inside there are great. All the points outside of there are suspicious. And then you generalize that to a 3-dimensional convex hull, a polyhedron. And there you have all these facets. And if you're inside this enclosure, you're great. If you're not, and beyond 3 dimensions, obviously I can't visualize, but if you're going to do this approach, you're going to have to do multi-dimensional kinds of things. And so the idea is simple. When I train, I take my computer system in the lab. I subject it to typical workloads. I get data that tells me what my system sensor should be like. I create a geometric enclosure around those. And then at runtime, I keep on monitoring those points, and if they're outside the boundary at any point, I start increasing my suspicion, and maybe I can measure things like the acceleration of how quickly they're leaving the convex enclosure, et cetera. And of course, there are techniques that we've developed, so if you exit the enclosure just a little bit, but then bounce right back in, it might be that your enclosure is not the perfect approximation, so there's sort of a fine art on when you actually declare that something went wrong. In terms of sensors, what are the things you can measure on a computer system? We measure a variety. One thing is we measure how many classes are loaded, how much memory is used, what is the depth of the runtime stack, right? And you look at that and you say, wow, that's kind of a weird thing to measure. But if you look at buffer overflow attacks, what happens? I'm running my program and I'm putting different functions on the stack. And then I modify the return address to jump to a particular piece of malicious code. Well, guess what happens to your runtime stack? It just freezes, right? Because you've now moved to a different part of the system and you're executing that malicious code. So instead of bouncing up and down and doing what it's expected to do, it sort of gets into this permanent state. So things like a stack depth average and counting your threads and whatnot are all great. And of course, the side effect here is that there is some performance penalty for measuring. That performance penalty is usually under 10%, okay, which is not horrible in the systems world. Later on, I'm going to talk about sensors that we're using that are actually already being used by your operating system to do measurements, in which case you're not really adding a lot of extra cost to do the measurement. But there is an associated cost. Your antivirus program doesn't do any of this stuff, right? It's not measuring stuff. It's not logging stuff. First simple example is we take nano HTTPD, which is a Java implementation of a web server. And what we're essentially doing is we're replaying logs of how people use this web server. And it turns out that this is the web server used by the Drexel computer science department, right? So we have lots of data for that. And so we can replicate what users are using, how they're using our web server. And we put the malware detector on the system and see what it does. And what we've done is we've created specific faults and malware that get injected onto this web server by basically sending a URL to the server. We send a URL to the server, and it knows to trigger a piece of malware. So that way we can measure when the malware actually starts executing on the system. We have lots of data. Some of the data we use to build our model, the convex hull model. Some of them we use to measure false alarms. So we want to replay that different data and see if it thinks that anything malicious happened when we know it didn't. And then we also have traffic data that we use once we subject the system to the malware and then see if it picks it up. So the kinds of malware we tried on this first experiment is we created a denial of service attack, we created a spam bot, so we wrote the malware. But we also wrote things that caused the program to do denial of service using infinite loops, infinite recursion, memory leaks, right? So if you know, most software systems that are running out there have memory leaks. And in fact, a lot of companies will will restart their malware periodically, even though nothing's wrong with their malware, their software periodically, even though nothing's wrong with it, because they know that there might be a memory leak there, and the longer you run it, the worse it gets. So let me see. And we have some results here. The results here, the green is the convex hull, and the yellow is the hyperrectangle, which is the more generous approximation. And if you look at the specific malware for infinite recursion, both of them were detected by both of these geometric models. Log explosion, which is a different kind of malware, similar results. Denial of service attack, the red bar represents when the software would have failed due to that denial of service attack. Both of those enclosures worked well. And the same thing for infinite loop, except that here you see that the convex hull was quicker in its detection. And then I want to move to some malware where you see there's no yellow bar, which means that only the convex hull was able to find that, that this was a problem. Same thing with infinite recursion, spam bot. And we were looking at the data and we said, well, how many sensors do you need in order to come up with these conclusions? And it turns out that depending on the malware, it's not always that one sensor goes haywire and you can say malware. It's often that you have to have combinations of sensors that go haywire at the same time in order to make the declaration of malware. So for spam bot, we found that the minimum number of metrics that change in order to make a detection is five different. And if you look at the different sensors, a lot of them look completely unrelated. CPU time and loaded class counts of the Java virtual machine. But as soon as you remove one of those sensors, it doesn't do the detection. So clearly there's some causal relationship between those sensors. So this was sort of preliminary work. Here's the false positive rate. Both of the systems have a false positive rate in these experiments of about 2.5%. That doesn't sound like much, but it could be. So it really depends on the cost of failure. If the cost of failure is huge, maybe you're living with this false positive rate. But if it's for a general purpose user, imagine that several days a year you got these false declarations from your antivirus saying you have malware when you didn't. So it depends. So what we wanted to do with the next work on using a statistical approach is answer the key question: can I trade off false positive rates for misdetections or false positive rates for time? How much, if I'm willing to live with the malware on my machine longer, maybe I could get my false positives rate to be lower. Okay, so we wanted to explore these trade-offs. And so we use quickest detection to do this. In quickest detection, you have a period. The nice thing about this technique is it doesn't require a lot of offline learning. You basically start this antivirus on your host, and it starts running. And then at some point in time, you get infected with malware. That's TI. And you want to find out what is the delta between the time you can make the detection and the time that there was a malware infection. It turns out that this is a parameter, and you can trade off that lag for accuracy. Okay? So here's the experimental test bed. So we have a host. The host has a hypervisor on it. It's actually a type 2 hypervisor, a software hypervisor. On there, we run a VM. On that, we run a host. And the idea for that is we want all of our detection technology to not be on the same OS as the thing we're monitoring, because the first thing that a clever piece of malware will do is disable all of those sensors, for example. So the process is we study everything on the guest OS. We look at kernel system calls, and we create a special detector for each one of those sensors that we create for the OS. And there's a data fusion center at the bottom, and there's some algorithm that says if I have a large number of detectors that go from no malware to malware, then I fuse them together and I can make a accurate and timely detection of malware. Okay, so I'm going to. Now, if you look at the sensors, we're talking about sensors on the order of 1,000 sensors. These are things that your operating system is already doing. The kernel is already making these system calls, and all we're doing is we're monitoring how many of these system calls it's making per unit of time. And it's very hairy and too detailed for this presentation. But the idea is quite simple. All right, so for any one of these sensors, I'm going to create a sequence of independent random variables. Okay, so I'm going to have sensor, the mth feature, the mth sensor is going to have measurements at time unit 1, 2, 3, up to ti minus 1, where ti is the time of the infection. And that data will have a distribution. And what I want to do is I want to find out after the infection if that distribution changes. And we found that if you can detect the change in the distribution after malware, you can quickly do a detection. And the algorithm for doing that is linear in complexity. So it's a very efficient algorithm. And essentially what you want to do is you want to see if the new data that occurred after the infection changes the distribution of your sensor data. And if it does it for lots of different sensors, then you can say with higher confidence that you have malware in your system. The algorithm that we use is Page's QSUM algorithm from 1958, I think. Here's the intuition. Well, here's the formula. It's a recursive formula, all right? So Gn is the value of the sum at time n. N minus 1 is the time period right before that. And then you take the log likelihood ratio, and that'll tell you if there's a change in the mean or in the variance. And if those are the only parameters that we're looking at in the distribution, there's a change in the mean and the variance that indicates a change in the distribution. And I think it'll become really obvious to you if I show you the diagram. So if you see down here, well, down in the green, QSUM is sort of bouncing around happily, and it's saying, okay, for this particular sensor, now this is the data for only one sensor, and we're going to have thousands of these running concurrently. As long as it's below that threshold, that black bar, it looks great. This is the infection time here, and as soon as the infection time happens, you'll see that the QSUM starts behaving a little bit differently. And in fact, at some point, it goes over the threshold boundary and takes off after that. So the idea here is if you have lots of sensors that are exhibiting this at the same moment in time, then you become increasingly suspicious and you say, oh, something strange is happening. And what you want to do is you want to minimize the detection lag time, right? And it's all about the trade-offs, right? Sometimes if you're, for example, a government agency where you want to detect the malware as soon as possible and you don't care if you have lots of false positive, but you want to make sure you get the malware quickly, it's different from maybe someone's laptop where you want to be a little more conservative. You can live with the malware for, let's say, 2 minutes, and that reduces your false positive rates to, we can make them close to 0, actually. Another way to look at the way QSUM works is if you look at this graph, you have the green points on one end, and these are this is the data that we gathered for one particular sensor before the infection time here, and then the red represents the data after the infection, and you'll see that the moving average is this guy over here, and the moving average seems to be doing just fine. Then the infection occurs, and you can see the moving average start taking off, right? So you're looking for those signals, those changes in distribution that cause those anomalies to sort of jump out from the data. All right, and the whole idea here is two things. One is you don't really have to do a lot of offline learning. Running the algorithm is computational very insignificant. The sensors that we get are data that the OS is already generating. So this is not something that's going to cripple the performance of your system. It's not something that's going to take a lot of machine learning or offline analysis. It's something that's very lightweight and can be used on a regular machine. So we did a lot of experiments, obviously, with this. This is the ROC curve of our experimental data. And you'll see that I didn't tell you how I got that threshold, right? That threshold is related to n, how many standard deviations away from the mean and the variance. But when n equals 1, you get the green line. It's green up there. When n equals 3, you get the blue line, which is the best one, actually. And that one has an area under the curve of 94%, which is pretty good. Ideally, you would want this to be 100%, where the line would be hugging the y-axis and sort of going all the way to 1 and across, right? That would be perfect. And it turns out that k, the parameter k, is related to our decision fusion engine, and that is how much agreement do we have to have? If we have 1,000 sensors, it turns out that if your k is around 20 or 30, you could do pretty good detection. So you just need to have about 30 sensors go haywire out of potentially 1,000 sensors in order to say there's something going wrong with your system. And that could be some memory leak or some presence of malware. If you look at the performance in terms of the detection lag, you'll find that we're only talking about something on the order of a few minutes, right? And in fact, 50% of your data has a performance lag of about 1.5 minutes. So that's pretty good. So when you're talking about detection here, you're not saying that I have to live with the malware for 24 hours before I give you a detection. I can live with it for 1.5 minutes and it'll give you a timely detection. I think that's very important. And that's a parameter as well. So again, if you can live with the malware longer, then obviously you can reduce your false positive rates.
Is this on the same data you trained by the session?
Right. This is for the same experiment as the one previously. This is just the performance angle of that. Now, I want to tell you that when we do this work, we're not subjecting it to known malware or anything like that. It's not dependent on seeing lots of different malware, using machine learning and saying, I have thousands of malware that I'm showing you, and next time you see something like that, all it does is anomaly detection. It's trying to characterize what's normal for your compute server or your mail server and finding changes to normal and reacting to changes to normal. So once you do that and you can make a binary decision, malware or not malware, then you can go to something more fancy like classification. And classification is like, well, what kind of malware is it, all right? What we did in this, and I don't have a huge amount of time, so I'm just going to sort of go over the highlights of this, is if you look at different vendors, and we looked at 3, Kaspersky, Microsoft, which is the MMPC, and McAfee, and you look at how they label malware, they use things like categories and families. Categories are things like it's a Trojan, or it's a worm, or it's a password stealer. And then families are things like it's Zbot, you know, some kind of family of malware. And they use different classification schemes for malware. They say, of course, they're all overlapping and they're not consistent, right? So what we wanted to do is we wanted to say, well, first of all, which naming scheme has the most interesting parameters for doing something like classification? It turns out that McAfee is a very simple one, where it throws a lot of different categories of malware together, and it makes classification obviously not that interesting. Microsoft has a lot more fine-grained nomenclature, and that's a little bit easier. What we do in the case of malware is, for each sensor, we have data, the green data, leading up to the malware infection, which is this lightning bolt. And then you have the data that's infected. And if you take the mean and variance of the good data, and then you look at the mean and variance of the bad data, and you normalize the mean change and the variance change, you get a new vector. And that vector tells you what happened, what is the change that is triggered by this presence of a malware. And then what we do is, since we know what malware did this, because we're doing this offline, we put the right label of that right next to it. So we take the Microsoft label or the Kaspersky label, and we associate it with that. And then we can build a decision tree. And the decision tree is basically, it's actually a forest, but I won't get into that, where you start out from those vectors, and once you go down to the bottom of the tree, you get specific malware, the top is the category and the bottom is the family. So it's a Trojan. Mare drop is the name of the family. Now, what does that mean? Well, here's yeah, I have one more minute. All right. So here are sort of the results that we got when we used the decision trees. It turns out that the best we could do is if we used Microsoft families as our labels, and we were able to accurately classify 66.8% of the malware. So once we knew there was malware, we could tell you with 66.8% accuracy which exact malware it is. Now, so this was an honest experiment in the sense that when we did all that training, it was on malware up to a specific date and time. Then in our suite of malware, because we have about 250,000 malware samples in the lab, we took malware after that date and we did classification on that malware. So we're looking at new malware, not obviously the malware we trained on, because that would be kind of silly and it would find everything. And to the point, we're making all of these classifications just by looking at things like OS system function call, kernel call distributions. None of this has anything to do with high-level things. It's all based on very low-level sensing. Okay, and here is the confusion matrix. I would have been very successful if all of these diagonals were solid black rectangles. Okay. And as you see, there are some cases where we have a lot of misclassifications. Now, this is, well, a lot of it is because we're not perfect in the technique. Some of it is that a lot of these malware do the same sort of thing. Okay, so even though they have different names or they belong to different families, they might be both botnets, and because they're doing botnetish things, the classifier can put them in different categories, okay? For things that were these polymorphic, metamorphic variants, however, we do extremely well. Because if you think about it, when they do the metamorphic and polymorphic transformations, they're usually semantics preserving. It's just changing the code so that it's hard to do the detection. So in that respect, we're doing fabulously well. Where we're not doing terrifically well is for new malware that's coming out that is sort of a combination of things. It might be a spy bot that's also, deleting some files on your machine. It might also be reading your cookies or sending them to somewhere. So these malware are not always very special purpose. Sometimes they're doing a lot of different things. And so when they come out, they don't neatly fit into a bucket necessarily. Now, if you use a technique like this in classification, you have to worry about long-term drift. So you want to make sure that you're periodically retraining so that you don't, because the malware developers are going to pick up on this and they're going to start creating new behavioral signatures, the malware doing completely new things to fool your system. So the point to leave is the talk with is, malware detection, behavioral malware detection is possible, classification is possible, but it's an arms race. We're creating this technology. The next step is the malware is going to change to beat this, and then we're going to change to beat that and keep on going. So it's a good research area to get into because you'll never run out of problems. All right, well, thank you. I'll take questions now.
Is it difficult to determine what may be buggy software that's not malware that's been added to a computer and actual malware?
Yeah, so that's a little bit of a philosophical question, right? So for example, if the server is buggy and it has a memory leak, and every 10 days it crashes and it destroys my e-commerce website, then that, is that distinguishable from malware that's, destroying your host? I think if you're just doing pure detection, there's no difference between failure and malware. If you're doing classification and there are behavioral signatures of things you've seen, then you can say either this is completely brand new malware that we've never seen anything like it before, or it might be a failing system. So in the short term, you could make the diagnosis that, this is probably failure because it's completely alien in terms of, how it looks. It's not, malware is rarely sort of revolutionary. It's very evolutionary. So you get a piece of malware, and then you get lots of variants of that, and people are modifying that. And so, yeah, you could probably make that distinction. Yes?
Do you need to have a clean system to begin with in order to train?
Good question. So all of these techniques presuppose that before you plug it in, that you spend some amount of time learning. And so if you look at the QSUM technique, it doesn't need a huge amount of learning time, but what we found is if you're working on, if you want to release a web server, for example, that you subject it to representative loads, that you pre-record traffic and you subject it to that so that the parameters could start being formed. When you ask how much learning you need, for something like the QSUM algorithm, if you have good test cases that can exercise the boundaries of what you want, you only need about 15 minutes of data. For the convex hull, we found that you need things sometimes on the order of weeks of data. And that's because when we were doing the computer science website, we found that that website is a completely different animal on Friday nights and Saturday nights and Sunday nights. Right? So which night do you think is the most busy night for a computer science department web server? Is it Friday night?
It'd be Sunday.
It'd be Sunday night, and indeed. So if you train on Sunday data, you don't need a lot of training. But if you were unlucky and you picked Friday to do your training, all you're going to find out is that you have a web server is something that is almost never used, right? Because everyone's out partying, I guess.
People install protective software of the kind you're talking about when they begin to worry that they've already been infected.
Yes.
And I don't quite see how I would do that. If I'm already infected, do I have to wipe the whole thing clean and start over?
So these techniques all presuppose that a model of normal has been created a priori. If you're running your computer now and you want to find out if you have malware on it now, you can use traditional antivirus and hope that the signatures were pushed on and that you don't have metamorphic or polymorphic malware, unlikely. Or if you do an inspection of the system, or you just don't trust it and you just have to wipe it and start from scratch. So that's, a disadvantage of the behavioral approach, because your software, if you put my tool on your machine, it's going to think that, the normal behavior is the initial behavior. That's.
So you mentioned at the end the sort of arms race idea, and I was wondering how far down the rabbit hole you've thought. So like if behavioral detection becomes the de facto standard, then I'm going to write a virus that does the same measurements you do and tries to maintain the state of the system.
Right.
So,
and then you start, yes, obviously we're thinking about things, but sometimes we're stealing ideas from the malware writers. So if they're going to do diversity as a way to protect their malware, we could do diversity in the measurements we make. So maybe instead of having always the same sensors, we have different sensors at different times of day or different days a week, or you can then do combinations of sensors, and those could also be things that mutate over time. So instead of measuring sensor S0, I take S0 multiplied by 3, divided by 2, and use that as a measurement. And on the next day, I change that. So obviously, there are more things. So yes, it's an arms race. Then they're going to figure out some other thing, and yeah. That's the next proposal. Yeah. All right, thank you.